Well, it's a great honor for me to be that my work is recorded in this way, and I am very grateful to the scientific committee and to the organizing committee. It's a great pleasure for me to be here in Rio. I'd like to thank all those who have persuaded me to come here to Rio, because I wasn't sure I would come. It's a pretty long flight from Israel to Rio. Well, I'm really moved by this presentation and by the honor it was made to me. Thank you very much again. My thanks go, of course, to Enrique for his help, to Luis Fernandez, and, of course, to Tudor and to Izu Vaisman, who were those who really persuaded me to come. Now, as for the lecture for the subject I'm going to present here, it's about Lie and courant algebroids on foliated manifolds, and unlike in the published papers, I will give you some references here and explain why I started to study this subject. Well, for Lie algebroids, we have, of course, the standard reference by Mackenzie's book. As for foliations, I will send to the book by Pierre Molyneux, Riemannian Foliations. Now, the starting point of my idea of studying the subject came from a paper by Laurent Jean-Goustier and Xu about holomorphic Poisson manifold and holomorphic symplectic algebroids. So the point was this: if you study differential geometry, usually you would like to look at three different categories. One is the C-infinity category, another one is the holomorphic category, and there is a third one which is less considered as such, but nevertheless it's important, the foliated category, where the objects are foliated manifolds and the morphisms are foliation-preserving mappings. And since everybody studies Lie algebroids and courant algebroids in the C-infinity category, and since the paper by Jean-Goustier and Xu started the same study in the holomorphic category, and since, on the other hand, among the many subjects I was interested in, and that were recalled by Tudor, also I was interested in foliations, it was just natural for me to ask questions about the same objects in the foliated category. This may also lead to the question of discussing Lie and courant algebroids on spaces of leaves of a foliation. And since the space of leaves of a foliation is a very bad object, then you look at the corresponding objects on the manifold itself and try to see what does not depend on the leaves. As for the various points of the lecture, there will be some question about integrability, where I use a paper by Mergic and Merchun on the integrability of Lie algebroids. There will be some discussions concerning cohomology, for which I have to quote an old book I published in 1973, where I discussed similar questions about cohomology of foliations. There will be some questions about characteristic classes, for which, of course, I sent to a paper by Luis Fernandez on Lie algebroids, holonomy and characteristic classes. There will be some point concerning the formation of this Lie algebroid foliations, this generalization of the foliations to the framework of Lie algebroids, where I follow an older paper by H, where the subject was discussed for foliated manifolds. For the courant algebroids, we have the basic paper by Liu, Weinstein, and Xu. As for the results I will be reporting here, they appear in two papers, and I gave the reference for the archive version, although the second has already appeared, and the first will appear in the Mediterranean Journal of Mathematics. And finally, I would like to add something of which I became aware later, namely that there is a paper by Olivier Brahic and Zhu about Lie algebroid fibrations. So it is not quite clear whether the Lie algebraic fibrations and the foliated Lie algebraids that I'm going to present here really overlap, but probably, at least in some cases, yes, which means the fibration should also be a foliation. Now I'm going to present the notion of foliated Lie algebraids. First of all, the framework for foliations, where the foliated category is considered as the C-infinity category again. By M, I denote the differentiable manifold. F is the foliation of n-dimensional leaves. And then if you have such a foliations, you always have local adapted coordinates that are denoted by xa and yu, where xa equals constant gives you the leaves of the foliation, and yu are coordinates along the leaves. I am going to use the term, the qualification foliated for every object which either descends to or is a lift of something from the space of leaves of the foliation, and I'm going to use the index FOL to denote such foliated objects. And of course, for the foliation, we have the exact sequence consisting of the tangent bundle of the leaves, of the tangent bundle of the manifold, and of the quotient bundle, which is here denoted by nu of f, and which is called the transversal bundle of the foliation. Now, there are some things which go over to this transversal bundle of the foliation. Namely, it is possible to speak of foliated vector fields. First of all, a vector field x of m is a foliated vector field if it is an infinitesimal automorphism of the foliation, which means the d bracket y x belongs to the leaves whenever y belongs to the leaves. And then I can speak about foliated cross sections of the transversal bundle, which are cross sections represented by foliated vector fields. And there also is an action of such foliated cross sections of the transversal bundle on foliated functions. So what are the foliated functions? These are functions that simply are constant along the leaves of the foliation. And also it is possible to get a bracket of foliated cross sections of the transversal vector bundle, which again is a foliated cross section of the transversal bundle. And then this situation of the transversal bundle is a prototype of what I call a transversal Lie algebroid on the foliated manifold MF. And this is just a foliated vector bundle E with a Lie algebra bracket on the foliated cross sections and with an anchor which goes not to the tangent bundle of the manifold but to the transversal bundle of the foliation. And the Lie algebroid, the usual Lie algebroid axioms are satisfied for foliated elements only, foliated cross sections and foliated functions only. So in order to see what this means, I shall note that if I have a transversal Lie, so the words that should be linked together are transversal and Lie. It means that I have the Lie properties in the transversal directions. So if he is a transversal Lie algebroid, then there are local projected bundles on local transversal manifolds of the foliation. Usually a foliation doesn't have a global transversal submanifold, but locally it always has such manifolds. And the fact that E is a foliated vector bundle means that there exists projected vector bundles, and these local projected vector bundles simply are Lie algebroids over the local quotient manifolds in the usual sense. And there is a particular case where, which is the simplest case, if the leaves of the foliation are connected and simply connected fibers of a submersion of M onto some manifold Q, then the whole structure projects to Q, and I simply get Lie algebroid over the quotient manifold Q. Now what I would like to look for are subalgebroids that would play the role of foliations for Lie algebroids. In the same way, usual foliations are subalgebroids of the tangent Lie algebroid of the manifold. And then, first of all, if I consider a pair of Lie algebroids, subalgebroid B of A, then if I look at the cross-section of the larger Lie algebroid A, I will say that it is foliated with respect to the subalgebroid B if for any cross-section B of the vector bundle B, the bracket, the Lie algebroid bracket between B and A stays in B. This generalizes exactly the situation encountered in the case of foliations. And in this case, I say that the cross-section A is foliated, and I get a space of foliated cross-section, which I am going to denote by gamma B of A, and it is very easy to see that this is a module over the foliated functions. If I take the product between a foliated function and the B-foliated cross-section of A, then I get again a B-foliated cross-section of A. And using these facts, I will define the notion of a foliation of a Lie algebroid. I say that B is a foliation of the Lie algebroid A if it satisfies two conditions. The first condition is that the restriction of the anchor of A to B sends B onto the tangent space of the foliations. And the second property is that the cross-sections of A are spanned locally by the foliated cross-sections. This is a condition I'm going to call the foliated generation condition. And then the pair AB is a foliated Lie algebroid. And furthermore, if the anchor sends B isomorphically onto the tangent bundle of the foliation, then I will say that this is a minimally foliated Lie algebroid. This reminds me that in Mackenzie's book, there is a notion of ideal systems of an ideal system of Lie algebroid, which is connected to this case, but it doesn't look at the second condition of foliated generation, and on the other hand, the first condition is less restrictive. B should only be sent into the tangent leaves, but here I have to ask it to be sent onto the tangent leaves. So this is the notion of a foliated Lie algebroid, and I have a very simple lemma which says that whenever I have such a Lie algebroid, and if I write A as a decomposition of B and of a complementary subbundle, then this complementary subbundle has local B foliated bases. There is the proof there, which is very simple. It's just a simple remark, but it's technically important because it allows me to work after that in a simpler way with foliated Lie algebroids. The first remark which I would like to make is that whenever B is a foliation of the Lie algebroid A, then the quotient vector bundle A over B is a transversal Lie algebroid in the sense of the first definition. Well, to see this, I just decompose A into B plus a complementary subbundle C, and I take the foliated bases of C that were given by the previous lemma, and then if I look at local bases and of transition functions between such local bases, and I use the definition of the notion of B foliatedness, then I see that the transition functions lambda have to be foliated functions, and this is exactly what produces a foliated structure in the quotient vector bundle. Because one of the ways to characterize the foliated vector bundle is to say that it has an atlas of local trivializations with foliated transition functions. Okay, and so I have the required foliated structure on the quotient bundle, and all the rest is just simple technical verifications, and then I get this result, which shows me that in the case of a foliated Lie algebroid, I get a diagram where on the line down I have the exact sequence of the foliation, and on the upper line I have a corresponding exact sequence for the foliated vector bundle. And in any case where I have some transversal Lie algebroid which I can include in such a diagram, then I would say that A is an extension of E, and in particular if B is isomorphic with F by the answer, then this is a minimal extension. And I'm mentioning this because in some results this will enter. Of course, the first question is whether there are good examples of foliated Lie algebroids. And there are such examples. Well, first of all, there's the trivial example of usual foliation, but a more interesting example is obtained in the case of a transitive Lie algebroid. If I consider the principal bundle, it is the classical construction of the transitive Lie algebroid. Now, in the particular case where the principal bundle is foliated, what does it mean? Again, it means that locally it projects onto the space of leaves of the foliation, or else that it has an atlas with local transition functions that are constant along the leaves. So if the principal bundle is foliated, and if I consider the construction, then I obtain, of course, the transitive Lie algebroid A, and if I, which is the usual quotientization process of the tangent bundle of P by the structure group G, and if I apply this construction only to the, okay, here I have to say something else. Whenever I have a principal foliated bundle, and more generally if I have a foliated bundle, it is always possible to lift the foliation from the basis to the total space of the bundle by just taking as leaves the covering spaces, the corresponding covering spaces of the leaves of the original foliation. And then T of P has this subbundle T of FP. FP is the foliation of the total space of the principal bundle P. And if I take this, I get a Lie subalgebroid, and I can check everything. The only difficulty is with the foliation, the foliated generation condition. But this is satisfied because it is satisfied for the quotient bundle TP over TFP, like for every foliation. TM over the tangent space of the foliation is always foliated bundle. It satisfies the foliated generation condition. And taking the quotient will not damage that. So this is satisfied. There is also another version of this construction in case of the principal frame bundle of a vector bundle. Namely, this is the, again, it's classical stuff in Mackenzie's book. Then the version is that the transitive algebroid is such that the cross sections are the differential operators of first order. And if I consider differential operators of a foliated symbol, then I get the subalgebroid and I get the corresponding structure. And another example, if I take a Dirac structure such that the Dirac structure, such that the foliation, I take a Dirac structure on M such that the tangent space of the leaves of the foliation are included in the Dirac structure. In this case, the bracket closure condition tells that the tangent vector fields of the foliation are infinitesimal automorphisms of D, and then the foliation, then the Dirac structure D descends to the space of leaves, and again the foliated generation conditions can be checked. So this provides other examples of foliated Lie algebra. Therefore, there are a lot of examples that can be given. There's another example here, which is again technical. If you take foliated Lie algebroid over the manifold M and you lift everything to the tangent, you get again foliated Lie algebroid. And finally, I would mention a construction which gives even more examples. Whenever one has a transversal Lie algebroid, which means a Lie algebroid in the foliated category, and whenever one considers a lift of the anchor, then there exists a canonical minimal extension of the tangent space of the foliation to a foliated Lie algebroid, which is here denoted by A0, and everything connected with this Lie algebroid has an index 0. And this canonical extension, which essentially is a class of new examples of foliated Lie algebroids, has well-defined bracket operation, has well-defined brackets and a well-defined anchor. And moreover, any minimal extension of E can be obtained in the same way, except that in the bracket there is some twist, which I am not going to explain in more detail. I'm going to skip the proof because time is running fast. Maybe if somebody wants, I just leave for a moment the transparency that contains the proof. So if anybody wants, he may just take a look at the proof there. Okay, the next question, which is quite natural, is whether it is possible to speak of the integration of such Lie algebroids. And it is not too complicated. To be able to speak of integrability, we have first to look at an adequate notion of a Lie groupoid. And this adequate notion of Lie groupoid is given by definition number 3 here. If I have a Lie groupoid over a foliated manifold, then I'm going to call this groupoid the foliated groupoid if at its turn it's endowed with a foliation, which is denoted by round G here, satisfying the following conditions. First of all, the leaves of the foliation G are contained in the left fibers, and these leaves are invariant by left translations. And secondly, the right projection, the target projection, the source projection, is a foliated leafwise submersion, and this means that the leaves of the foliation G are sent by R onto leaves of F, and this projection is always a submersion along the leaves. And if I use this notion, it is easy to prove by using the paper on the integrability of Lie subalgebroids by Mergic and Machun, and which gives me the following result. Suppose that you have a foliated Lie groupoid, then the Lie algebroid A of G is a foliated Lie algebroid. And conversely, if you have a foliated Lie algebroid and if the Lie algebroid A is integrable to a Lie groupoid, then the Lie groupoid has a natural foliation, making it into a foliated Lie algebroid, and such that the leaves of this foliation precisely produce the subalgebroid, that is the foliation of the Lie algebroid A. And again, there are some words about the proof of this result. Essentially, I already told you some of the ideas, so I will not explain the proof in any more detail, except that in order to check the foliated generation condition, you need that condition that the target projection is a submersion along the leaves of the foliation. That much about integrability. And then the next subject that I would like to describe a little bit is cohomology and characteristic classes of foliated Lie algebroids. And well, essentially the pattern that will be obtained is that of the foliations, but expressed in a corresponding convenient way. If I have a Lie algebroid A, of course, the cohomology of the Lie algebroid A is just the cohomology of the cochain complex obtained by looking at what can be called the A forms, which means cross sections of the wedge products of various degrees of the dual vector bundle A star with the usual differential, which is the exterior differential in the sense of Lie algebroids. Now, if I consider the situation of a foliated Lie algebroid, I get a pattern which was known in the case of usual foliations, namely, it is very convenient technically to consider again a decomposition of the Lie algebroid A as a direct sum of the subalgebroid B, defining the foliation, and the complementary subspace. And in this case, I have the possibility to look at local bases of A that consist of cross sections of B and of B foliated cross sections of C, and of course the dual basis. And then the differential, the A forms get double grading. It is possible to say that an A form lambda is of type SR if the local expression of this form lambda is the local expression that is marked there, and this is invariant by changes of by changes of local bases of the same type, of course. And the point is that in this case, the exterior differential in the sense of the Lie algebroid A gets a decomposition into three terms that have the corresponding types 1, 0, 0, 1, and 2, minus 1, which means the type is increased respectively by 1, 0, 0, 1, and 2, minus 1. And then this produces a lot of structure inside the cohomology of A. First of all, the operator, which is here denoted by D double prime A, which is essentially the exterior differential along the foliation of the Lie algebroid, this gives a cohomology which is nothing else than the cohomology of the subalgebroid B. On the other hand, there is so-called basic cohomology, which is the cohomology that is transversal to the foliation. And Furthermore, it is possible to define the corresponding filtration and to get the corresponding spectral sequence, which essentially is the same configuration that was known in the case of a foliation. I would like to mention two types of Poincaré lemma which occur in the situation of minimally foliated Lie algebroids. The first Poincaré lemma that I look at is something about the operator d double prime. And the result is that if a pair AB is a minimally foliated Lie algebroid, then for any local A-form lambda of type UV, where V is larger than 0, such that d double prime lambda is 0, locally lambda is exact with respect to the operator d double prime. Locally one has lambda is d double prime of mu. And the essence of the proof is an induction on the index k, where lambda, the local expression of lambda, does not contain the elements a star k plus 1, a star k, a star q, q being the codimension of the foliation, the elements of the local basis. And for the case of k equals 0, the Poincaré lemma for the operator d double prime is just the Poincaré lemma for the exterior differential along the leaves, and this was proven by myself essentially sometimes in the late 60s, so it's a very old result. This is why I quoted the book from 73, because the lemma, this Poincaré lemma is there. And then for the induction process, it's just technique, a little bit of computation, which you see on the screen, and which gives you the result. And now a similar Poincaré lemma holds, of course, whenever I look at forms, at A forms with values in a foliated vector bundle. And then there is a standard corollary. I am able to look at sheaves of germs, of forms, of B-evaluated forms with values in the vector bundle V, and then because of the Poincaré lemma, I can compute the cohomology. There is another element of this pattern which I believe is new even for foliations. Namely, it is possible to look at another interesting subcomplex of the A forms, which is given by what I call the U truncated forms. And the space of the U truncated forms is defined by the situation where I look at A forms with a decomposition into homogeneous type, into homogeneous components, doesn't go up to the end, but only up to the first index equal to U. Generally, I should go up to the first index equal to the codimension of the foliation. And then I can also define a corresponding differential, corresponding coboundary, by cutting out the unnecessary terms from this truncated forms. And then I get a lot of cohomology spaces associated with the foliated Lie algebroids, which should be seen as intermediate cohomology. For the index U equals 0, you get the cohomology of the subalgebroid B, and for the index U equals to the rank of the bundle A, you get the whole cohomology. So you have a whole scale of intermediate cohomologies. And the interesting point is that, again, in the case of the minimally foliated algebroids, there is a Poincaré lemma for this operator DUA. Therefore, again, you are able to compute some cohomology spaces of some sheaves. I have the proof of the ideas of the proof of this Poincaré lemma, but again, by looking at my watch, I will not explain this proof in detail. It's again an induction process that has to be carried over. Now I'm going to say only a few words about characteristic classes. Rui Fernandez has transposed the Chern-Weil theory to Lie algebroids. And it is also possible to transfer the whole Chern-Weil theory in order to produce not just characteristic classes, but also secondary characteristic classes for a foliated Lie algebroid. So for that, one has to consider the notion of an A connection, which is nowadays very well known. I'm looking at covariant derivatives. So instead of taking covariant derivatives in the usual sense, you take them with respect to a Lie algebroid, and then it is possible to consider the Chern-Weil procedure to look at invariant polynomials, at any invariant polynomial phi in invariant polynomials for the general linear group, and to evaluate this on the curvature of the connection. And it is possible to repeat in a convenient way Butt's calculation to get the formula giving the difference between phi evaluated for the curvatures of two connections. This shows that it is possible to define the principal characteristic classes, and these principal characteristic classes do not depend on the choice of the connection. This is classical Chern-Weil procedure, so I'm not going to insist on that anymore. But furthermore, it is possible to define also the notion of a Butt connection. A Butt connection for a foliated Lie algebroid AB is just a connection of the Lie algebroid A satisfying the condition that the covariant derivative nabla in the direction of an element belonging to the Lie algebroid B and of a foliated cross-section V of A should be 0. This is just the definition of a Butt connection. It is easy to construct such Butt connections, and then it is possible to repeat Butt's argument to see that if you are in the situation of a characteristic class defined by a polynomial in the degree larger than the codimension of the foliation, then this characteristic class must be 0, simply because if you plug in the curvature, you get too many factors of the same type, and then the result simply has to vanish. And this leads to a corollary showing that not always subalgebroids are expected to be foliations. If you have a subalgebroid, a Lie subalgebroid B over Lie algebroid A, and if the vector bundle has a non-zero characteristic class in the wrong dimension, then you don't have the situation of a foliation, which means that essentially the foliated generation condition is not satisfied, may not be satisfied. I do not have concrete examples of this type. It would be interesting to have such concrete examples, but at least in principle, you shouldn't expect any Lie subalgebroid to be a foliation of the Lie algebroid. And then you go one step further. Whenever you have a foliated vector bundle and you look at an invariant polynomial of odd degree 2h minus 1, which is large enough such as to to go over the codimension of the foliation, then the two terms in the right-hand side, the two terms in the left-hand side of Butt's formula for the difference vanish, and then you get a closed form which defines a cohomology class, and this type of classes are the secondary characteristic classes in this situation. What happens is that the secondary characteristic classes of a foliated Lie algebroid obtained in this way are images by the homomorphism induced by the anchor of the RAM secondary characteristic classes of the foliation F. So perhaps it would be desirable to have another more construction of secondary characteristic classes, giving classes that are not images of usual secondary characteristic classes. But this is again an open question for the moment. Another subject I have considered for foliated Lie algebroids is deformations. And again, the pattern encountered in the theory of foliations will appear, which means that we will be able to define infinitesimal deformations of a deformation of the foliation. So first of all, what do I mean by a deformation of a foliation B of a Lie algebroid A? This would be a family of foliations, so a family of Lie subalgebroids defined, say, for a parameter t between 0 and 1, such that B0 is B, and such that each subalgebroid is projected by the anchor onto some foliation, so it's a regular Lie subalgebroid, such that the foliations Ft define the deformation of the foliation F. And I should explain what I mean by differentiability of this family with respect to x and t, and this is explained here. Simply, you must have local bases that are differentiable with respect to the two variables x and t. And then, if you have such local bases and you look at the transition, you discover that you may define one form with values in the quotient bundle A over B, which is defined by taking the derivative with respect to t for t equals 0 and quotientizing with respect to B. And that you get this form psi. And the point is that this form is independent of the, well, in the definition, so this is a form, so you have to express the psi for one vector B. And to do this, you extend the vector B to a cross-section. And then you have to prove that it is independent of the extension. Well, there are some technical computations to be performed here, which in the end will give you the result. So to prove the fact that psi does not depend on the extension, you will look at a complementary space which is complementary not just to B but to the deformation of B for small values of t, and then you get bases which are more convenient to work with, and you may compute in another way this form psi, and then you may identify the form psi with the form which is here denoted by psi with an index c, which is that instead of looking at the form with values in the quotient bundle A over B, you choose a complementary subspace C and you identify the quotient bundle with this complementary subbundle. And then you get another formula for the psi, and this formula shows this formula is no more dependent on the extension of B. I'm aware of the fact that the proofs cannot be followed at this speed, but I have no choice. This is the... And again, like in the case of foliations, we have to define a notion of a trivial deformation of a foliation, of the algebraic foliation. And by a trivial deformation, I mean a deformation which is defined by a flow, let's say, given with respect to a cross-section A of the algebroid A, capital A, which means that the derivative of the action of this exponential on another cross-section is just the bracket, the algebroid bracket. And once this is done, it is possible to do some computations about the infinitesimal deformation form xi, proving that for a trivial deformation this is an exact form. And after that, the notion, like in foliation theory, the notion is extended, triviality is introduced in the definition of deformations by looking at the notion of equivalent deformations. Equivalent deformations meaning that we have two deformations such that they differ from one another by a trivial deformation. And in that case, the two infinitesimal forms, the two infinitesimal deformation forms will be cohomologous with respect to the cohomology of B, and then the corresponding cohomology class is the infinitesimal deformation, and then, like in the case of the foliations, the space, the cohomology space H1 of the Lie algebroid B with values in the foliated vector bundle A over B, this is the space of infinitesimal deformations of the foliation. Now I went at this speed because I thought it will be more interesting to touch upon the second subject, which is courant algebroids, the notion of a foliation in the framework of courant algebroids. The first step is the same. I will define the notion of a transversal courant algebroid over a foliated manifold MF. And this will be a foliated vector bundle with a non-degenerate foliated metric and an anchor sending me to the transversal bundle of the foliation. But this time, both the anchor and the bracket are defined only for foliated elements. They are not defined for all the cross sections and for all the functions, but only for foliated functions. And then the axioms of the courant algebroid, I am using the skew-symmetric version. The axioms of the courant algebroid are satisfied only for foliated elements. So this gives me the notion of a transversal courant algebroid, which essentially is the object playing the role of a courant algebroid over a space of leaves of the foliation. And again, in the case of a submersion, submersion which has connected and simply connected fibers, this configuration projects to the courant algebroid on the quotient manifold. Now, it is again possible to define the notion of a foliate cross-section of a courant algebroid A, but this time with respect to an isotropic subbundle that is closed by brackets. And moreover, this notion is coherent only for the case of the orthogonal coisotropic subbundle of the isotropic bundle B. And with these precautions, the notion of a foliated cross-section of B with respect to C is defined like in the case of the Lie algebroids. I am again asking that for every cross-section B of the subalgebroid and for the indicated cross-section C of the orthogonal bundle, the bracket, the Courant bracket BC belongs to gamma. Well, I usually, well, let me put also the next transparency. Usually this bracket BC this always happens, belongs to gamma C. But if I want the section C to be foliated, I ask it to stay in the space of the cross sections of the subbundle B. And again, I have the possibility to define the notion of a foliation of a Courant algebroid. This time, a foliation of the Courant algebroid A will be an isotropic subbundle B with the property Z. So I said B is isotropic. It is closed under the Courant bracket operation. It is projected by the anchor onto the leaves of the foliation. And I must have some more properties. If I look at orthogonal bundle C of B, this is locally spanned by the foliated cross sections. And the metric, the scalar product with respect to the metric of two foliated sections must be required to be again a foliated function. And in this case, I say that the pair AB is a foliated Courant algebroid. Well, again, it is possible to prove that the quotient bundle will be a transversal Courant algebroid. And I am not going to explain this, but I would like to explain that that there are examples, there are enough examples of foliated Courant algebroids in this sense to make us consider that the notion has some interest. By T big of M, I denote the Whitney sum between the tangent bundle and the cotangent bundle. And it is classical, I do not have to explain this for the present audience, that this is a Courant algebroid with respect to the structure defined in Ted Courant's thesis. If I also have a foliation F on the base manifold M, then the orthogonal, then this foliation is an isotropic subbundle of the big tangent bundle, and if I look at the orthogonal space, this orthogonal space is simply Tm plus the annihilator of the space F, and it is not very difficult to check the foliated generation condition and to see that a classical foliation is also a foliation of the Courant structure of the big tangent bundle. Another example is given is obtained if I consider a two-form, a closed two-form theta, and I consider the graph of the musical homomorphism flat defined by this form theta, and then again it is possible to check the foliated generation condition. So this graph again defines an example, gives an example of foliated Courant algebroids. But maybe another thing is a little bit more interesting. and this will be the last thing I'm going to explain, I can prove the following proposition. Suppose that E is a transversal courant algebroid over a manifold MF. And let us consider any complementary subbundle of the tangent bundle of the foliation, which is denoted here by Q. Then it is possible to construct a natural extension of the transversal courant algebroid to a foliated courant algebroid, capital A, such that B is isomorphic to F. So whenever you have a courant algebroid over the space of leaves of the foliations, so to speak, then you can extend it to a foliated courant algebroid over the whole manifold. And the sketch of the proof is as follows. The extension will be defined. First of all, if I have the foliation F, the direct sum between F and its dual bundle can be made into a courant algebroid in exactly the same way as courant's classical algebroid. Because if you have a foliated manifold, you may look at the manifold with a different differentiable structure, namely the structure where the manifold is the sum of the leaves. And then you may apply the definitions given by Courant, and then check that whenever differentiability holds globally, it also holds for the results. So you get this structure on F plus F star, and you get the corresponding Courant algebroid, which is denoted by a round Q, a calligraphic Q here. And then you take the direct sum between this Q and the given transversal Courant algebroid E. And then you have to pay attention of how to define brackets. And if you study the structure of the Courant brackets in the classical example of Courant for the situation where the manifold has a foliation, you are going to discover what your Lie brackets must be, what your Courant brackets must be. And the Courant brackets must be given by this formulas, which you see here. And it's very long and tedious to check the axioms and to see that everything works. This is in the second paper for which I gave the address on the archive. So if anybody is interested, he or she should just look at that paper. And here I'll just stop here. I already am 3 minutes late, I believe.